Hi there! Whether this is new for you or just a review, welcome to the fundamentals of logic, and I hope you don't mind, I'm sitting down to record these now. This is part 4, so if you haven't seen our previous videos and you aren't already familiar with logic, you should probably go and check those out first, because in this video we're going to get even more abstract. So far, we've seen how truth tables can show us validity, they can show us that something is valid, but they can't always show us the details of why it is valid. To see more, we're going to move away from language completely and just look at the syntax of our arguments. This system is called natural deduction, although it does have several other names. To be clear, in this video, we do not care about the content of any premises at all. We are only looking at the form of the argument, and we can change this form and still preserve validity. We're going to come back to natural language in the next video with some examples. There are a few. Actually, there are a lot of different ways to write out natural deduction. It's annoying, so I will be using this book, which is Logic, an Introductory Course by W.H. Newton Smith. It's a book that I was familiar with about 20 years ago and then didn't open, and it's the one I've been using to prepare for this course. So a lot of what I do will be based on his notation, which has some good and some bad things. But as I've said before, you will see different versions of this content, and we may have a little look at some of those in a bonus video. We'll start from where we defined an argument last time. An argument is a set of premises which all together support a conclusion. There are many different ways to write out an argument, but we have been writing them as a sequent. We take each of the premises, separate it with a comma, and that is the left-hand side. We then use the double turnstile to introduce the conclusion on the right-hand side, a little bit like the equals in a maths equation. We can also write any argument out as an expression in our logical language. Each premise is put in conjunction with the others, and this is the antecedent of a conditional, and our conclusion is the consequent of that conditional. This is called the corresponding conditional of an argument, and if that corresponding conditional is a tautology, then the argument can never ever lead from true premises to a false conclusion, no matter what the premises are. However, you can still have untrue premises in the first place, so just because you have a valid argument, it doesn't mean that the conclusion is good. The best arguments are sound arguments, where you have a valid argument that uses premises that have confirmed to be true. We mentioned before that syntax is the system of how words go together to make statements, and sometimes words go together in similar ways to make similar statements. They have the same syntax. For example, we can see quite easily that these two arguments here have the same syntax, even though one of them is about pizza and one is about world peace. However, in both cases, they are saying if one thing happens, then the other happens. The first thing happened, therefore the second thing happened. We don't need to analyze the content of the premises at all to see that, and so we can see that the syntax is the same for both arguments. So we can see that the symbols we have chosen to represent our arguments are also showing us the syntax of the argument. In this case, it's showing us that these arguments are both modus ponens. With the right set of rules, we can change these expressions in ways that preserve truth. We can test for validity using only syntax. These rules will change the expression by adding or removing connectives, so we will call them introduction and elimination rules. This is the process of natural deduction, and it has some advantages and disadvantages over the truth table method. Now that we are dealing with only syntax, we're going to use a different symbol to conclude our arguments, and that is the single turnstile, also called the syntactic turnstile. The single turnstile can roughly be read as therefore just like the double, but it actually shows a different kind of entailment. The double turnstile claims that the entailment from premises to conclusion comes out of the meaning of the words. The single turnstile says that the conclusion can be derived from the form of the premises. We do need to remember that natural deduction has been developed from natural language terms like and or but, so there is some crossover between these two types of conclusion, but they do conclude in subtly different ways. So let's look at these truth-preserving rules for syntactic analysis, shall we? These rules will add or remove connectives from an expression one step at a time. These rules preserve truth. If the premises we start out with are true, then anything we derive with the rules, as long as we apply them correctly, has to be true. For some of these rules, it will be obvious how it preserves truth. For others, it will be trickier. I hope my explanations are clear, but if not, or if you think I've made a mistake somewhere, which is completely possible, then please let me know below. Our first rule is the conjunction elimination, and it's fairly straightforward. The conjunction says that both A and B are true. So if the conjunction A and B is true, it must also be true to say that A alone is true or B alone is true. This eliminates the conjunction because we can now go on to use A alone or B alone as true lines in our argument. So great, we've used our rule to change our expressions. But if we're going to make much more complex arguments, we're going to need a way to show all of these steps that we're taking and show that all of these steps are valid. What does that look like? There are, once again, many different ways of recording syntactic validity, even in table form. But for our system, each line of our derivation will be recorded on a new line of a table. The table has 4 columns. The first column shows which premises need to support this step. Only premises will appear in this column, although not all premises are needed for every step, and we will see with some rules we can actually remove premises from the argument. The second column records the step number of the derivation, and in the third column we record the expression that we have derived at this step. The fourth column is where we put all the steps we've used in this step and the rule that we have used to make this derivation. Each rule is cited with its symbol along with an E or I for elimination or introduction respectively. We'll also see something called the proof spine, which is a way of keeping track of our conclusions. There was a lot there, and if all of that is unclear to you the first time, then please do not worry. Have a look at some of the examples with me, try and follow through them, and then come back to this description, and hopefully it'll make a bit more sense the second time through. Something else to warn you about, I will talk about the rules using letters from the beginning of the alphabet, A, B, C, etc. But the examples we'll look at will use P, Q, R, and so on. Typically, letters from the beginning of the alphabet are more abstract in use. They are used when showing form, and letters from the middle of the alphabet stand for actual statements in arguments. This can obviously be confusing. Sorry about that, and I will explain more in a moment. There is a reason. I just want to let you know to watch out for that before we start. So let's show the conjunction elimination rule in this way. We're going to start from step 1. And this is our premise. We assume that it is true, so it does not rely on anything else in this argument. We show this by writing P or PR in column 1, then the step number, and then in column 3 we write the expression that we're starting from, P and Q. We don't need to cite any rule for our premises, so nothing is needed in column 4. We now move on to step 2. We're going to derive from the premise in step 1, so this is our supporting premise in column 1. Then step 2, and we are deriving the simple statement P. This is what goes in column 3. We're deriving it from the expression in step 1 and using the conjunction elimination rule. So this is what we put in column 4 to show our process. Of course, we could use the conjunction elimination rule to derive Q alone instead. The process would be exactly the same. It just depends which statement we wish to derive. Finally, the proof spine shows where our premises are divided from anything we derive. The vertical line is our main argument and goes down the middle of our table between the second and third columns. And we draw a horizontal line under our premises before anything we derive. With this rule then, we can see that we have shown the sequence that P and Q entails P alone or Q alone. The proof spine will become more important when we start to look at subproofs. The second rule is the conjunction introduction, and it is also fairly straightforward. If we already have two things that are both true, A and B, then we can derive the conjunction of them, A and B. And natural language shows this. A and B are true, and we can just change the verb form from are to is. Looking at the syntactic table, we can see that we now need two premises to make this rule work. Step 1 and 2 are those premises, P alone and Q alone, and then we can use the conjunction introduction rule to move to step 3, which is the conjunction P and Q. This conclusion rests on both premise 1 and 2 being true, so we record them in column 1, and we've also used both those lines in this step, so we record them along with the rule in column 4. Again, there are two versions here because we could equally well derive Q and P. Of course, that is logically equivalent to P and Q, so it doesn't usually matter. The order of the premises is not important, and it doesn't really matter which premise you assign to which letter. But once you have named each premise with a letter, you must always use the same letter for the same premise. This might seem obvious, but it's surprising how easy it is to make a mistake like this. Notice that so far our examples have been extremely simple, but the expressions we use in these rules can be more complex than just a single letter. Here is another example of the conjunction introduction rule, but in this example, our letter A is the disjunction P or R, and we're using the conjunction introduction to connect that disjunction to B, the simple statement Q. This is one reason why we have to show our rules as one set of letters and then the examples of the rules as a different set of letters, because the examples can be more complicated than the rules alone. The negation elimination is next, which is a lot of fun to say. It's also another quite easy rule. A negation says that something is not true. But if it is not true, then it is true. In formal terms, the negation elimination says that if we can derive not A, then we can derive A. The two nots just cancel each other out. There isn't much to the syntactic table here. We just move from not A to A, and we cite the rule and the line number we are on. Not A is actually logically equivalent to A, so I hope in this case the truth preservation is fairly clear. This rule is so clear from natural language that it may be something you learned about in school as the double negative in English lessons, and some systems of logic call this the double negative elimination. This actually leads us to a bonus rule, which is the double negative introduction. Not clear when you'll need to use this, but if you have A, then it is valid to derive not A. So far, in all of our rules, it's been fairly clear how they preserve truth from our natural language examples, but that is about to change. Coming to the more complex rules, we'll soon see that it's sometimes useful to use one of our premises again in later lines of our argument. Fortunately, it is truth-preserving to give a premise or another line again at a later point in the argument. This is called the rule of reiteration or restating, and it allows us to make a new line which matches one of our previous lines. The exception here is you cannot reiterate something outside its subproof, and we'll see what that means in just a moment. Here then, we can see that anything we have derived and not already negated can be reintroduced at a later line in our argument. You can reiterate something inside a subproof, but as we said above, not outside. But what the heck is a subproof? The system of natural deduction can actually be quite creative. There are many different ways we can go that are equally truth-preserving, and sometimes we might want to bring in a new premise to help us get to certain conclusions. Again, this seems a bit strange, like we are cheating. We aren't, but it does again show us how making a valid argument does not immediately make you automatically right. But what we are doing is using a set of rules that definitely preserve truth. Whenever we choose a new premise for our argument, we call it a hypothesis or an assumption, and our derivation now depends on that too. This starts a subproof, and we can now continue our derivation just like before, but eventually we must try and remove this hypothesis from dependence. In other words, we must finish the subproof to get back to our main conclusion. If we do not do this, then the hypothesis has technically become a full premise. In the next rule of the negation introduction, we'll see both reiteration and hypothesis helping us to complete our derivation. So there's no getting away from it. The negation introduction is a complicated rule. We cannot just say that we are negating a statement and expect this to preserve truth. If we want to negate an expression validly, then we must show that that expression leads to something that cannot be true. In other words, we must show that it leads to a logical contradiction. This might be something like A and not A. So if we can use one of our premises to derive a contradiction, then we can reject that premise. This is also called reductio ad absurdum. Using this rule, we will derive the sequent that P entails not P and not Q. We can explain this sequent quite easily in natural language. If you know that one of these things is true, it cannot be true that both are false. However, it does seem strange to derive such a long conclusion from a single letter expression, but we can do it and preserve truth, but it will take us quite a few steps to get there. I will talk through this derivation, but as these get more and more complex, it will probably be easier for you to stop and read through the derivation step by step rather than listen to me. And feel free to take it slowly and go through each step one at a time, trying to see how truth is preserved at each stage. We start off with our single premise, P, but there is no rule which lets us move directly to our conclusion. Our intuitive understanding is not truth-preserving. So we have to make a hypothesis that will help us get to our conclusion. This is sometimes also called an auxiliary premise. In line 2, we give this hypothesis. We assume that not P and not Q is true. We assume that both the things are false. We label this premise as H for hypothesis, and we start a subproof, which is shown by adding a second proof spine where we make the hypothesis. This subproof depends on our hypothesis and our main premises. We want to use our premise P again, so we will reiterate it inside the subproof. We then use the conjunction elimination rule to extract not P alone from the hypothesis. We now have both P and not P. So we use the conjunction introduction to derive the contradiction, and this is the end of our subproof. Now that we have shown that our hypothesis leads to a contradiction, given that we already know P, we can use the negation introduction to reject it. Note that we could equally validly just agree with line 4 and reject the premise on line 1. This would have been a different proof, but it would have been a valid use of the not introduction rule. It all depends on what we're trying to prove, and that depends on the content of the premises, which we are not discussing here. So we saw above that a subproof is like an argument inside an argument based on a new premise or a hypothesis. All subproofs should be finished because they bring in premises that are not part of our original sequent. It is possible that the hypothesis could be accepted as a full premise and then added on to the sequent, but this is not the goal of subproofs. We don't usually want to add premises if we don't need to. There's no rule for when you need a subproof. It's up to you to decide when you think introducing a hypothesis can help you to derive the conclusion you are aiming at. As I said, you should think about logic and most more abstract mathematics as a more creative activity than the arithmetic or the probability that you learned in school. Although it does still have some rules, of course. Another trick is to say at the beginning of a subproof which rule you plan to use to end it. So on line 3 of our previous slide, we would have written the negation introduction rule next to our hypothesis to show that's what we wanted to use to end the subproof. We will see this and other notes that we can add to our process column to make our work clearer, and other people will no doubt have their own sets of symbols. This is probably why there are so many different systems and styles of recording logic. The subproof spine begins at our hypothesis and it continues until we are ready to complete the subproof. The next line should not depend on the hypothesis. The horizontal line again divides the premises from the conclusions. This will often come immediately after your hypothesis, but in the example above I included the reiterated premise P before moving on to derive not P. In some systems, you don't really have to restate the premise every time. We could just cite it in from line 1, but it does make sure that our subproof is complete in itself, and it's useful for being careful when you're first doing these kinds of derivations. Now we come to the conditional elimination, and this rule is much easier than the last one as long as you understand modus ponens. The conditional elimination basically removes the consequent from a conditional by using modus ponens to do this. If we have a conditional, if A then B, and we know that the premise A is also true, then we can validly move to B alone. We saw modus ponens in a previous video, so let's look at a slightly more complex version. If P, then Q. If Q, then R. P, therefore R. By using the conditional elimination twice, we can first derive Q alone, and then use that to derive R alone. Notice that we use different lines for each step, but the final conclusion depends on all three premises. This extended version is sometimes called modus ponendo ponens, which I suppose is a way of affirming the affirmation. So now on to the conditional introduction, and things start to get trickier again. If we want to introduce a conditional, then we must show that some premise A entails something. To put it formally, if we can derive B from premise A, we show that B depends on A, and so that A is sufficient for B, which is the conditional. This allows us to validly derive the conditional if A then B. The conditional introduction can validly follow directly from our last example. Our conclusion R rests on P at line 3, as well as two other premises as well. So we can, as our next step, introduce the conditional if P, then R. But something interesting happens. Our final line does not rest on premise P at line 3. Why not? Well, I'll oversimplify it here, but this is where you must use the perfect tense from school. We must have already derived a complete proof of B from A using our truth-preserving rules. We could not have used the introduction rule if we did not. Now that we have done this, we do not need A to be true for if A then B to be true. This definitely feels a bit like climbing the ladder and then throwing it away. On to the disjunction introduction, and this rule may be the simplest one of them all. It is so simple, in fact, it seems like a trick. If you have some premise A, then it is truth-preserving to introduce a disjunction with A and any other premise you like. It's not difficult to see that this works according to the truth tables, but it does seem strange on some level. Our second premise can be anything at all. Why? For the purposes of preserving truth syntactically, it simply does not matter. But that's not the same thing as saying it doesn't matter at all when we bring the semantics in. Any child can use the disjunction introduction rule when they say, or it could not be bedtime. But that doesn't mean it isn't bedtime. Once again, a valid argument is not always a sound argument. Here we can see the disjunction introduction as the sequent P, therefore P or Q. As with all of the rules in this video, we're seeing only a simplified argument of only the rule itself. In the next video, we'll explore some full derivations employing multiple rules at the same time. Here though, it is once again just a single step to go from P to P or Q. This does preserve truth, so we will never go from true premises to a false conclusion. But I will say again, it is only sound if P is actually true, and then this sequent would be a sound argument. And if the disjunction introduction is the simplest rule, then the disjunction elimination is by far the most complicated. The disjunction elimination needs twice as much work as all the other rules because you are deriving two things. A disjunction has the syntax A or B, meaning at least one of the simple statements is true. We know that. Now, if we can go on to derive a third thing, C, from A alone and from B alone, then we can conclude that C is true because A or B is true, not either one of the individual premises. The disjunction elimination preserves truth because no matter whether A is true or B is true, the disjunction can still derive C. Disjunction elimination perhaps isn't the best name, to be fair. What we're really eliminating is dependence on the individual premises. But there is a sense in saying after the rule has been applied, the or does not matter anymore. We're using a slightly more complex expression now. This sequence states that P or Q and R is true, and therefore that both P or Q and P or R are also true. This sequence is something we can probably see as true by looking at the form, but there's not a quick and easy way to explain it in natural language. In this table, what we can do is assume that P is true as a hypothesis, and then we can use the disjunction introduction rule twice to bring in both P or Q and P or R, and then the conjunction introduction rule to put those together. This way we've moved from one side of the disjunction to the conclusion. Before we can use the disjunction elimination rule though, we must derive our conclusion from the other disjunct. This is a parallel subproof that we will do in a second table, but it is a continuation of the same main proof, so we continue numbering. This time we start with Q and R as a premise, and we can use the conjunction elimination to get Q alone and R alone. Then we can use the disjunction introduction again to bring in P or Q and P or R and put them together as before. So we can see that lines 5 and 11 are the ends of two independent subproofs. We've derived our intended conclusion in two ways, corresponding to line 2 and line 6. We can now finally use the disjunction elimination rule to claim that our conclusion actually depends on line 1, the original disjunction. There is something strange here. We have not actually eliminated the disjunction, and like I said, it perhaps isn't the best name. Our conclusion rests on the original disjunction. This can be a bit confusing, and there are other naming systems which call it by a different name for exactly this reason. What we have eliminated is the need to worry about which disjunct is actually true. The disjunction elimination is quite confusing and it's difficult to get clear in your head. Be careful, do plenty of examples. Here is one example that might make it easier to catch on to, but I don't have a perfect way to explain it. Sorry. But imagine that you know it is either Monday or Wednesday. For some reason, you know it's true that it is Monday or Wednesday, but you don't know which one. Let's say you also know that Adam goes running on Monday and Wednesday. So you still don't know whether it's Monday or Wednesday, but what do you now know? Pause if you want to think about that, but you now know that Adam is running today. It now does not matter how the disjunction is resolved. You know that Adam is running today because he runs on both the days that it could be. This is how the disjunction is eliminated. The disjunction elimination preserves truth because no matter which out of A or B is true in the disjunction, we can still derive C. Note, you have still not resolved the disjunction in any way. You still have no idea whether it is Monday or Wednesday. You've just made it irrelevant to the conclusion that Adam is running. If this rule is still hazy, then don't worry about it and do try some examples. One final quick example that might resonate with modern humans though. Either I am at home or I am not at home. If I am at home, I have my phone. If I am not at home, I have my phone. Therefore, I have my phone. Sigh? For our final connective, we will introduce both rules together because they are simply the reverse of each other, and we've actually seen them before. When we learned about the biconditional, we learned that it is the conjunction of two conditionals with a reversed antecedent and consequent. And the rules are exactly this. The biconditional elimination means that if we have the biconditional A if and only if B, then we can simply replace that with the conjunction of those reversed conditionals. And the biconditional introduction says that if we can derive the conjunction of those reverse conditionals, then we can simply validly move to the biconditional. This rule shows clearly that the purpose of these rules is often to rewrite the expression in a form which does not use a certain connective, so that we can move towards an outcome that we want. Both rules for the biconditional can be shown on a single line. We simply move from the biconditional to the conjunction of conditionals, or vice versa. These two are logically equivalent, so clearly this rule preserves truth, and it pretty much is that simple. However, don't think that means that you will ever have a derivation where you start with a biconditional and finish with the conjunction of conditionals. This rule, when you use it, will simply be a step in moving from one part of your derivation to another. Here we can see a summary of all the rules we've looked at. Of course, it skips some of the details, but it's an aid to memory once you start to use these rules for yourself. Notice that 3 of the rules can remove premises from the support column: the negation introduction, conditional introduction, and disjunctional elimination. These will be useful next time in deriving different types of arguments. We will stop there, and just to sum up, in this video we've introduced all the basic rules for natural deduction and shown how each of them preserves truth when we use them. We've seen several different sequences which represent simple arguments, but we've not done a real derivation of a real argument from natural language. We'll look at this next time along with several other important mechanics of deduction. As always, it's essential that you do some examples and exercises to help you understand this better. And don't be afraid if you come across explanations which look very different to mine, because you will. And maybe one of these explanations will help you understand it better than mine. Either way though, I hope that this introduction to the rules of natural deduction has been useful for you. Hi, hope you found that interesting. Like, comment, subscribe, etc. If you prefer shorter videos, you can find this cut up on our other channel just up there. But whatever you do, please keep learning something, because no matter who you are or how old you are, every day really is a school day. Bye for now.